All right, and we're live. Okay. Hello, everyone, and happy Wednesday. Welcome back to another episode of PyTorch Community Voices. So it's a weekly webinar where folks from our PyTorch community get to come up and showcase how they use PyTorch and what they've built in PyTorch. So I am your host, one of your hosts today. I'm Jessica, a developer advocate here at Facebook, focused on our AI ML open source projects.
And hey everyone, my name is Suraj. I am a developer and a developer advocate at Facebook AI, and I work closely with PyTorch.
Nice. And today, we're really excited to have our guest, Fernando from TorchIO today. So for a quick background, for those who don't know, TorchIO is an open source Python library used for medical image preprocessing and augmentation. TorchIO was developed to help researchers standardize the medical image processing pipeline and really allow them to just focus on the deep learning aspects. All right, so with that, I'm going to bring Fernando up onto the screen.
Hello.
Hello.
Hi, Jessica, Suraj. Thanks for the introduction.
Yeah.
Welcome, Fernando.
Welcome. Would you be able to give a quick introduction of yourself?
Yes, so I'm Fernando. I'm a PhD candidate at University College London and King's College London. Working mostly on, I work mostly on epilepsy, AI applied to epilepsy videos and MRI. And yeah, I'm looking forward to sharing this thing. Thank you very much for the opportunity.
Nice.
Of course. Thanks for joining us today, Fernando. Usually the the outline of the show is the first 15-20 minutes is all yours. So you run through your presentation, and today we'll be hearing about TorchIO from you. Meanwhile, our audience will be chatting in their questions for you. And once you're done with your presentation, we'll open up the floor to questions from the audience. And Jessica and I have some questions of our own, and we'll be interrogating you with those as well.
That's good.
The audience, a quick reminder, while Fernando is presenting, please feel free to drop in your questions in the chat. We are live on Facebook, on Twitch, and on YouTube. Post in your questions, and Fernando is really happy to answer all of them.
All right, so with that, if you're ready, we will hand the floor over to you.
All right. Thank you. Thanks, Jessica. Thanks, Suraj. Okay, so well, the presentation is you can download it in Figshare. Here's the DOI. It will be shown at the end again. And here's the website for the documentation if you want to take a look. So first, to describe what TorchIO is, I think it's easier to describe what it's not. It's not a deep learning framework. For example, PyTorch, PyTorch Lightning, Monai. And the easiest way to explain what I mean is neural networks are never used within TorchIO. TorchIO can be used for researchers that want to do stuff with neural networks, but basically for everything else that happens around the learning itself. So what is it? It's a Python library for loading, preprocessing, augmentation, and patch-based training of medical images in deep learning. And I will be explaining all this stuff along this presentation. TorchIO is part of the PyTorch ecosystem. So you can find it on the PyTorch website, and you'll see, I'll show here that is very compatible with other libraries from the ecosystem. Why do we need something like TorchIO? Well, in medical images, we don't have a lot of annotated data. First, because it's very time consuming to annotate 3D medical images for segmentation, for example, as we can see on this video. Moreover, we need typically highly trained annotators for the data, such as radiologists, and this is very expensive. Also, patient privacy needs to be preserved. So it's relatively hard to be able, or it's rare to be able to share patient data to the open world to be used for training. That means that few annotated data sets are available in general, and therefore augmentation is very useful and probably needed as well. Another reason is that medical images are not just an array of pixels or voxels for 3D, they are considered physical objects in the space. So they have some spatial metadata associated that needs to be taken into account. For example, they have an origin with respect to a system, to a reference. They have a certain orientation, so the sequences of pixels are not necessarily parallel to the reference I just mentioned. And they have a spacing associated. That means that, well, pixels in general in images are considered to be square, whereas in medical images they can be, they typically are a rectangle, cuboid, if they are 3D. So all these information needs to be taken into account. Here's an example of one MRI 2D slice of one magnetic resonance image, and we have also a corresponding segmentation of the same size. We open them in medical image software such as 3D Slicer, and we see that they correspond to each other perfectly well. And this is because medical image software understands all the spatial metadata. But if this metadata is ignored, then the results can be catastrophic. So training will not work probably if all this data or metadata is ignored. Therefore, we need domain specialized libraries to deal with this kind of data. Also, computational costs are a big issue in medical images. Typically, for example, we have a little a little image that, for example, could be from ImageNet, used to train a network for image classification of RGB images, and that's about 0.5 megabytes. Here we have a typical CT scan, which is about 550 times larger than the image. That's typically a challenge in terms of GPU memory. That's about these many cats compared to the other one. So we need to deal with somehow, especially if we want a batch size larger than 1. So let me talk a little bit about the code first, actually. The library can be installed using, it's of course open source. Python library can be installed using the pip package manager. All the code is open on GitHub with links to the documentation, etc. There is continuous integration, continuous deployment. The documentation is built automatically after each push in the repository. The code is checked automatically for coverage, for quality, etc. Of course, and then talk a little bit about the community. So we have a growing number of contributors in the community, either with bugs or documentation, code, ITS, etc. It keeps growing. Everyone's of course very welcome to open a discussion in the repository to add a feature or fix a bug or whatever they would like to do. The number of stars in the repository keeps growing, so people seem to like the code, and we have quite a lot of downloads per week. So it looks that people are interested in it. This, of course, doesn't necessarily mean that people are doing useful things with TorchIO, right? So let's actually look at something a bit more tangible. We wrote a little preprint last year in winter about the library, which has been actually accepted for publication in a journal today, this morning. And it looks like people are actually using TorchIO for the research because they are referencing the paper in the publications. If we look at what people are doing with TorchIO, we can see that there's a lot of segmentation, a lot of brain MRI as well, and a lot of self-supervised learning, which I think it's very exciting. And when I saw this at the beginning, I thought maybe the library is too biased to brain MRI. But then I looked at data from Mikai last year. There was a word cloud that someone made, and it's very similar. Segmentation, we see brain MRI. So hopefully this reflects the interests of the community, not necessarily a bias of the library. We can see here some examples of what people are doing with TorchIO. So top left, we see correction of artifacts from MRI. Then variation autoencoder used to fuse multimodal imaging. We see segmentation of neonatal brain MRI, segmentation of lesions and healthy tissue. But not everything is brain MRI, as I said. So we have also a lot of interesting research, self-supervised learning from CT scans, transformers applied to medical image classification, detection of COVID on CT chest CT scans, cardiac segmentation from MRI, analysis of continual learning on prostate MRI. So I think it's actually quite diverse, and even some more exotic applications such as in vivo tracking of glial cells or segmentation of seismic fascias. I think this is very cool and exciting. So about the library itself, well, first let's take a quick look at the API. It's actually very, very similar to Torch Vision, and we've tried to be as Pythonic and PyTorchic as possible. You can see that Torch Vision on the left and TorchIO on the right look quite similar, and we've done this on purpose. And people, we've received a lot of feedback from people saying that it's very, very easy to learn TorchIO, and that's a great thing to hear actually from users. The architecture, the library is based basically on PyTorch, NumPy, SimpleITK, and NiPBel. So SimpleITK and NiPBel are medical image libraries used a lot for I/O, but also for the preprocessing and augmentation. I'll talk a little bit about the interfaces later, but for now, the most important modules in the library are data and the transforms module, which I will present now. So this is the typical data structures used for training. We have the subjects dataset, which inherits directly from the PyTorch dataset and contains basically a list of instances of subject. Each subject typically contains some images, and then, of course, arbitrary data about the subject's age, diagnosis, and subject. Could be not necessarily a human, right? It could be a mouse or whatever. And then there are two main types of images in TorchIO. Scalar images can be used to store any images with continuous data. In this case, it's a diffusion MRI. There are 40 images, which can obviously generalization. They can be 2D as well, always with the spatial metadata associated, plus any arbitrary metadata needed for the image. The typical training pipeline. This is very similar to Torch Vision. So there is a data set, and when it is queried for a subject, the images of the subject are loaded from the disk. They are pre-processed, augmented. Basically, the transforms are applied to it, and these happens in parallel thanks to the PyTorch data loader. After that, TorchIO's job finishes, and it's everything else happens, right? But this is all TorchIO's job. But as I said before, sometimes volumes are too large, so we need something else, right? So typically something that's done is training with sub-volumes instead of the full volume, also called patches or windows. And here the first part is like the previous one in the previous slide, but then the processed volumes are stored, well, they're processed in parallel, but then there is a sampler that randomly extracts patches from the volumes that have been processed according to some specified rule. And then instead of one patch, which is not very efficient, many patches are sampled from each subject, and they are stored in a buffer or a queue. And then another PyTorch data loader is used to pop the patches from the list and collate the batches of patches. Sorry, it's a bit confusing. But that's how we solve the big volumes issue. And of course, the other big part of the library is the transforms that can be classified according to whether they're used for pre-processing or augmentation. So pre-processing transforms are typically deterministic, whereas augmentation are random, as we can see from the names. And then we can classify the transforms into spatial or intensity. And we'll see an example of that in a second. Basically, spatial transforms modify the position of the voxels, whereas intensity modify the values. So here's an example of a spatial transform applied to an image. And of course, the same transform is applied to scalar image and the corresponding label one in this case, using the appropriate interpolation type for each image. Whereas the intensity transforms are only applied to scalar images, because it wouldn't make sense to add noise to categorical labels. And all this is done handled automatically by TorchIO. Something very special about TorchIO is we have some MRI-specific transforms, augmentation transforms. For example, simulation of inhomogeneities in the magnetic field of the magnetic resonance machine, or simulation of motion, patient motion artifacts, simulation of RF coil spikes artifacts in the machine, or ghosting artifacts. And these, basically using these during training makes the model very robust against this type of artifacts from the input images. TorchIO is very easy to extend thanks to the lambda transform that takes a callable, which takes and returns a PyTorch tensor. But then here's an example of a transform that we wrote to simulate resections, brain resection on healthy brains. And yeah, there are many examples of transforms that users have been developing. PyTorch is extremely modular. All the components are separated quite well, so that makes it very easy to mix it with other libraries that use PyTorch, especially libraries from the PyTorch ecosystem. For example, we have our latest tutorial, which I really recommend, uses TorchIO, Monai, and Lightning at the same time. So in this case, TorchIO is used for loading, preprocessing, augmentation. Then the network architectures, losses, and metrics are used. So network architectures, losses, and metrics from Monai are used for training. And then instead of writing boilerplate code for the training loop, PyTorch Lightning does all this work for us. So yeah, I really recommend this tutorial, which you can find easily in the website, in the documentation. Transforms can be composed, not just linearly, but according to the probabilities that they get. A graph can be generated like this with just 3 statements. So in this case, for example, we want the input image. Half the images will be augmented using a spatial transform, but we want the randomifying to happen 80% of the times, and the elastic deformation to happen only 20% of the times, because randomifying is much faster, therefore making the library or the pipeline more efficient. And then we want to rescale the intensity of all the images. All right, so this is intensity normalization. Something that TorchIO focuses a lot on is on reproducibility, and we want all experiments to be reproduced exactly the same. So it works very well with TorchIO, with PyTorch, random number generators, etc. The seed can be set at the beginning. You'll have the same augmentation again, because all random numbers are handled by PyTorch. And then also it's important to trace. So for example, this is training curve where we can see some spikes, and we would like to know what happened. So what happened in this batch? Why was my loss so bad? And this might have happened 3 days ago in the middle of the night, etc. So we would like, if possible, to log all the transforms that have been applied to our data, and this can be done easily with TorchIO. So here's an example of some of a set of transforms that have been composed and applied to some subject, and we can see that all the parameters, the parameters that have been used for the augmentation, are actually stored in the output, and we can very easily recover that transform and apply it to the same subject again, and then maybe we'll see what was wrong during that iteration that made our loss be so high. Invertibility of the transforms is also important. Why? So test time augmentation and uncertainty estimation is a hot topic also in medical images. So what these are is basically what happens is there's an image and a spatial transform is applied, a random spatial transform is applied to it multiple times, and then inference is performed on the transformed images instead of the original image. So we have a set of images in different spaces of inferences. Then we need the inverse transforms to put the inferred images in the original space. And then we can use, for example, an average of the inference to have a robust result. That would be test time augmentation. And also we can use, for example, the standard deviation of the entropy of all the predictions to estimate the aleatoric uncertainty. Therefore, it's important that the transforms are invertible, or as invertible as possible. So here we have the example from before. We have subject. We apply some random transform that we can recover with the tracing system that I mentioned before. And then with just a single line with a method, we recover the opposite transform, the inverse, right? So if crop was the last thing, then pat is the first, etc. Of course, not everything can be recovered perfectly, but we have one method to apply the inverse transform again, and we can see that the original image has been recovered as well as possible. There are so there is a datasets module as well, which is very similar to the datasets module of Torch Vision. Basically, there are external datasets that can be very easily downloadable using TorchIO, either to play around with the library, or there are actually some really big datasets that can be used for research, for training. I will just talk a little bit more there. So there's not just the Python interface, but we have also a command line interface that can be used, for example, to write batch scripts. This is useful for pre-processing of large data sets, or for example, to try different parameters for random augmentations, for random transforms. Although for that application, I would recommend, instead of the command line interface, I would recommend the graphical user interface, the GUI, which is implemented as an extension for 3D Slicer. And here you can see that there's a randomifying, and you can change the parameters manually and apply the transform and see what maybe if I do translation, too much degrees maybe of rotation, that's not what I like, so let me change that in my code after seeing what it looks like on Slicer. And this, the good thing about this is that there is no coding, and the extension can be installed just with your mouse, going to the extensions index of Slicer and clicking on install on any platform, in theory. So getting started in TorchIO, how would you learn? So as I said, it's very easily installed with just using the pip package manager. There are a number of tutorials that are available from the documentation or from the repository. And these tutorials, you can see lots of different things: normalization, pre-processing, spatial transforms applied to intensity applied to RGB images, histology, 2D, 4D, 3D. There are full training pipelines for in this case for segmentation. We have some estimation of aleatoric uncertainty as well in the tutorials. So I recommend that you take a look at those. And of course, at the documentation, we hopefully is very detailed. You can see exactly what each parameter of each transform does, etc. And just to conclude, some limitations of TorchIO are that, well, it's slightly biased towards 3D brain MRI segmentation, despite what I said about the interests of the community, mostly because it's what I've been doing a lot in my own research. Therefore, we welcome a lot contributors that can contribute with, for example, simulation of CT scan artifacts, ultrasound, different types of MRI, diffusion, functional, PET, SPECT, 2D, histology, and then, of course, for other tasks, not just segmentation. So other transforms that would probably be useful for regression or registration. So yeah, it would be great to have more of that in the library. And for similar reasons, the RGB support is not as as important as in other libraries. I mentioned that in a second. Something else is that transforms are applied on CPU. This is mostly a limitation of the libraries that are used under the hood. Although I think this is not that relevant because I think augmentation, loading, etc., is typically performed on CPU. And this also makes most transforms not differentiable, which is something that's useful, for example, in registration for deep learning or in spatial transformer networks. But to overcome these limitations, these three limitations at the end, I recommend, there are many other fantastic libraries in the PyTorch ecosystem that you can use to overcome these challenges or these limitations. And that's it. That's all I had to say. Thank you very much, and I'll be happy to reply to all your questions.
Wow, thank you so much, Fernando. That was an incredible presentation. I have never worked with medical images, but now I'm inspired to do some hacking of my own over here. For folks who are just joining us, we had Fernando present on TorchIO. He walked us through the library and how it can be used for deep learning and medical imaging. We are taking questions in the chat, so please feel free to pose in whatever queries you might have on TorchIO or your own medical imaging projects, and Fernando is here to answer them.
Nice. Well, yeah, so we're in the segment of the talk where, we're going to ask some questions. So while we're waiting for, so we do have some questions from our audience. So to kick us off, though, I'd actually like to ask, can you explain the story behind the name TorchIO? Because it's a medical, obviously a medical project, but I don't really see medical in the name itself.
Yes, I agree. The name is not very informative, unfortunately. So what happened is that at the beginning, about 1.5 years ago, I was using a lot NIFNet, which is a TensorFlow-based framework for medical images and deep learning. Then I started looking at PyTorch as everyone else, and of course I wanted to use it, and I wanted to see some of those features in PyTorch. So I created my little library that basically was using the I/O features of NiftyNet in PyTorch. So that's why TorchIO. Then I started sharing it with my colleagues, and then I put it online. I created the pip package, and well, with all the momentum now, it's a bit too late. But yeah, that's where it comes from.
Well, I think that's a good problem to have. It kind of grew beyond the scope of what you thought.
Yeah. So today, actually, someone said that maybe Torch, because it's similar to Torch Vision, something like Torch Med Vision, Torch Medical Vision would have been. But I mean, what can I do?
Yeah, it's okay. There's a story there. Nice. So with that, how about let's just start jumping into some of our viewers' questions. Let's see. There's one from Khadija here. I'm sorry if I'm mispronouncing your name. So I'll just read it out loud. Hi, I have a question. Working on the classification of medical images, I have 3 regions of the same image, and I want to do a classification of these regions into 2 classes, healthy or pathological. Can you propose to me a method? Do you have any suggestions of where maybe to start off, how to think about this?
I am trying to understand the image. I have 3 regions of same images, so I don't know. What classification of this region to 2 classes? I assume these might be histology images, and there have been labeled densely labeled into pathological or healthy tissue. I'm going to assume that. And for that, I think something like patch-based sampling would be useful, because then patch could be extracted from these potentially huge images, and then one could use samplers to sample more often from the pathological tissue, for example. And yeah, I think so what I recommend is look into the patch-based training tutorials.
Okay. That's a good suggestion. Nice. How about Suraj? I think you have a question.
Yeah, I do have a question. You just mentioned patch-based sampling, and
Yes.
I realize that medical images can be huge, and quite often downsampling them is not an option. But this also creates a lot more memory requirements when you're loading the images in batches. Can you tell us a little more about how TorchIO deals with this problem or this challenge, and how does patch sampling work?
So yeah, so as you said, so for the first part of your question, as you said, sometimes it's not possible to downsample the images. So it depends, right? If you're segmenting the, for example, for segmentation, if you're segmenting the brain, maybe you can do with pixels that are a bit larger than the original ones. But if you're segmenting the cochlea, for example, you need a lot of resolution for it. Therefore, you probably don't want any downsampling. The problem with that, as you said, is huge volumes. And for that, we use patches. And the way it works is very similar to NiftyNet. It's basically a probability map is generated or can be passed to the samplers to decide which voxels are going to be sampled more often. And for example, for the case of Khadija that asked, you could generate a probability map to sample, let's say, 50% of the times region 1, and 25% from region 2, and 25 from background, because you want to focus a lot on region 1. Sample a voxel means that voxel will be the center of a patch during training. Hopefully, and then we have different types of samplers in TorchIO. So there's the uniform sampler, where all voxels have the same probability of being sampled. We have the label sampler. So for example, if we have 4 different labels in, again, let's say segmentation of chest CT, we have left lung, right lung, spleen, etc. We can sample each label with the same probability.
Okay.
So even if it's a small structure, such as spleen, smaller than the liver, you can decide to sample both as often. And then we have the weighted sampler, which takes an arbitrary probability map. That's a superclass of the uniform and the label.
And all of this is built into TorchIO. Like, this is all available out of the box.
Of course, yeah. And that's shown in the the tutorial I recommended before. If you Google TorchIO patch training, you'll find the tutorial.
Yeah, thanks.
Thanks, Suraj.
All right, so in our next question here, I will not attempt to pronounce the name, but Fernando, thank you again for a great presentation. Is there any performance tests or comparisons between PyTorch data loader and pre-processing versus TorchIO?
So I think what Nikita means is that, well, they're actually the same thing, because TorchIO is very, very tightly coupled with PyTorch data loader and pre-processing. So PyTorch data loader and pre-processing. So there is no real pre-processing section in PyTorch, right? One can use the functional or the transform to do pre-processing, but everything is quite generic, which makes sense. But TorchIO does use this stuff. TorchIO uses everything in TorchIO is PyTorch, as I said, or NumPy or SampleDK, etc. And the data loader is something that one typically uses independently TorchIO. So yeah, so it's basically we don't need any comparisons because everything is the same thing.
Makes sense. Also, do you speak multiple languages? I noticed that you're able to pronounce the previous.
I went to Serbia last year, and I decided to learn Cyrillic on the plane.
Oh,
so
wow.
I can read, but I don't understand.
Oh wow, that's cool. Let's see. So we have a number of other questions. Let's make sure we answer all our viewers' questions. Any support for M1 on Macs?
Do you know what that is?
Maybe this is. I thought maybe this was some.
I don't think if it's something related to medical. I don't know.
Okay.
M1 Max. Oh, I think I see what's going on. Is this maybe? I'm googling this, but it says it's an ARM-based system on a chip. Maybe it's related to the new Apple chips that are meant to be very fast without a GPU. I'm not sure, but this would be the PyTorch guy's job, not mine. So this is lower level.
I see. Yeah, and if Rishi, if you have any other information to add for this one, please add that. Oh, so yeah, some people are saying it's M1 chips on Macs.
Oops.
Cool.
Oh, I see.
Yeah, thank you. Let's see. Let's jump to Thomas. It says, great talk. Do you have any plans to support batch GPU augmentation? In my experience, that has helped particularly with large images, CTs, etc.
Okay, I think I see what Thomas means. Yes, actually, there is an open issue on TorchIO about supporting GPU augmentation as much as possible. And I think what they mean is, for example, when there is a batch that has been collated from the queue or from the data loader that is connected to the queue, that batch is made of PyTorch tensors that can be just thrown into the GPU. And I guess sometimes, so for example, it wouldn't make a lot of sense to perform, or maybe it's not a very good idea to perform rotation of a patch, because there will be a lot of black, right? That's why we perform the rotation of the whole volume and then we crop. But things like adding noise or blurring, I think, especially for example, something like blurring, where it can be performed very efficiently with convolutions, I suppose. Yeah, it would be very interesting to have that on GPUs, and that's definitely something that we're looking into. So that's a very good question.
Cool. Yeah, thanks, Thomas, for that question. I was going to hand it off to Saraj. Do you have another question? I think yours.
I do.
Okay.
Fernando, you mentioned in your talk about how the community has been growing by leaps and bounds. And I was wondering if you had anything to say or any suggestions for potential contributors. I know a lot of people in our audience would be keen to know how they can possibly work on contributing anything to TorchIO. Can you tell us a little more about what kind of contributions TorchIO is looking for? How can people be more active in the community?
Yes. So thanks, Suraj. Well, first thing, I guess it depends on the type of contribution, but everything can be a contribution, right? Like giving feedback about it, what you think, what you like, what you don't like, fixing a typo in the documentation. And if there's something more serious that they would like to address, so I would recommend to read the contributing guide, which is available on their repository. There's a lot of instructions that for everything that needs to be done, which is not that much. It's just a standard contributing pipeline, right? And then open a discussion, open an issue. We'll discuss everything there, and yeah, that would be. And as I said, contributors that do not work on brain MRI segmentation would be great, so that the library is a bit more diverse. And then for, not necessarily contributions, but you mentioned about the community. So we're very happy to even explain basics of medical imaging. Some people are struggling because so something I would like to see, I guess, is more forums on medical images online. There's the PyTorch forum. There's I guess, I don't know, maybe it exists, but something like a Stack Exchange of medical images. So now people are asking questions in the TorchIO repository, in the Monai repository, in the PyTorch forum. But I think it would be nice to have a bit of a stronger or more open community in medical images.
Maybe you should start a Slack for this.
Yes, there is. I mean, there is Slack. There's a Slack for TorchIO, etc. But I feel like the problem with Slack is that I don't think it's meant for questions that can help others in the future, like Stack Overflow, for example. I don't know if that makes sense.
Yeah. So like it's there, people can go refer back to it.
Yeah, exactly. So
like a knowledge base, right?
Mm-hmm.
Yes, something that someone will be able to Google in 20 years. Some Slack where you have to sign in, etc., etc.
Yeah. Well, Thomas is shouting exclaiming in the comments that yes, he'd love to see more TorchIO in the PyTorch forum specifically. But also, I think maybe today is the day that one of these aggregation sites of places that people can come together and like have these discussions specifically about medical images. Be interesting. Yeah.
Yusuf has a question on patching, on selecting patches. He asks, what is the best strategy to select patches from MRI images? Would you recommend selecting random patches, all of them, or some guided selection of the patches? Thanks, Yusuf, for your question.
Okay, that's a good question. A bit specific, but I like it because I worked on this right before I started my PhD. So MRA means I think MR, so magnetic resonance angiographic images. Basically, it's MRIs where you can see, hopefully, only the vessels, brain vessels. This is a very challenging problem, especially because, for supervised learning, it's really, 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 really hard and annoying to label by hand all the vessels in 3D. So it's very annoying in 2D, but in 3D, it's
on a whole other dimension.
Yes. It's not lines, it's dots, it's ellipses you see everywhere. And obviously for one single image, you can take many hours. So, and also vessels are very small sometimes, therefore you need a very high resolutions. And so we used to work with CT scans of resolution of 0.5 millimeter, which is quite small for human. And I did try with different types of samplers. And in my experience, using weighted sampler to sample more often from the vessels, but not only, was the best. And a way to create those probability maps is just it could just be the label map, or you could generate a probability map using, for example, a distance transform, which for those who are not familiar, it just means an image where each voxel or the value of each, let's say, pixel represents the distance to the closest pixel that is a 1 instead of a 0 in the input image. I hope that will help. That will help Yusuf.
All right, so let's jump to like a broader scope topic. Sudamaze from Twitch asked, are you aiming to have TorchIO work as a general pre-processing library? Is there any thoughts on that, or like focus on medical imaging? Just focus on.
That's a good question, because I think I saw Fernando present about some seismic images and the analysis of rocks, which are not very medical.
Yeah. So, to my background is in engineering, but my more recent background is in medical image computing, and more specifically 3D medical image computing. So that's what I had in mind. But then, I realized there's a lot of other images that are not, a lot of multidimensional images that are not necessarily medical. And I mean, many of the functionalities can be, obviously, as you say, Suraj, can already be applied to any type of, for example, astronomical data, seismic, stack of histology data, what else? Multispectral data. So this is cameras that don't have just RGB, but a lot of images from the spectrum. So yeah, for example, the random affine transform, or the random elastic transformation, which is what they used extensively in the seismic study. Those are pretty generic. So maybe that's a good opportunity to get a better usage of this of the name of the library, and get away a bit of the medical and generalize for just multidimensional data, really.
Nice. Well,
Interesting.
Yeah, that's a good observation there. Oh, sorry. So I actually just clicked on this question here. So I guess we'll ask the question. Sohara from Alam, he says, "Hi Fernando, nice discussion. Let's see. While using TorchIO transform, all my CPU cores, 64 cores, got occupied, and I want that. Is there a way to restrict it?"
So yeah, I mean, I will need to look a bit closer into it. So this would be probably a good question for the you could open an issue or a discussion in the GitHub repository. But if you're using a lot of cores, maybe you set the number of workers in the data loader to 64, and that's what's happening. In which case, you can just set it to something lower, like 10, I suppose. But yeah, I recommend you open an issue, Sarwar.
Yeah, seems like a very case specific. So
yes, it is. Yeah.
Look there. All right. So how about I think Suraj had the last question to round out this presentation with.
Yeah, I wanted to go a little broader now, like stepping back from TorchIO. I was wondering if there was something that you would want to change in PyTorch. What would that be?
Well, that's a bit of a difficult question because I'm a big fan.
That's why I saved it for the end.
Related to the challenges that I mentioned at the beginning, in terms of patient privacy that needs to be preserved, and the scarcity of annotated data sets. There are some fields of machine learning that I haven't had the time to learn a lot about, but in terms of privacy, federated learning is something I'm very excited about, where so the data doesn't have to leave the hospital. The images just stay there, and then the model is sent everywhere, right? And it's updated everywhere, and then comes back. So privacy is very, very well preserved. And then related to that, things like self-supervised learning, where annotations are not needed, or weakly supervised learning, where the clinicians would be able to annotate images much faster, would help a lot, I think, the federated learning pipelines. So I guess seeing higher and higher level features related to these worlds, federated learning, self-supervised learning, weakly supervised learning, would, from a selfish point of view, I think they would be very helpful for us, for the medical imaging community. So I suppose that's something. Hopefully, in the next, the next 2 to 5 years, there will be a bit of that in PyTorch.
That's a great answer. It is a feature that PyTorch is also taking very seriously, with it just makes more sense, right? To send the model out rather than get the data from everywhere and centralize the processing and the decisioning.
It makes a lot of sense, and I think it's a low-hanging fruit. And if I now I'm in my last year of PhD, but if I had to start again, I would just follow those routes. I think, because I think it's very interesting, very important, and it's just there. So of course it needs a lot of infrastructure as well.
Yes.
But that's something here at King's they're working a lot with NVIDIA for that, for example, and I think that's very promising.
That was a difficult question, but thanks for sharing your insight on that.
Thank you very much. Thanks, Suresh.
Cool. Yeah, thanks, Fernando, for your time. So with that, we know we're a little bit over time, but thank you all who are watching across the interwebs, YouTube, Facebook, Twitch. Yeah, very excited to have you all coming in and asking all these great questions. So yeah, welcome. Thanks again, Fernando, for taking the time to be here.
It's been a pleasure. Thanks for the opportunity.
Yeah,
it's been a pleasure.
Yeah, if you are watching, please make sure to like or subscribe so then you can stay notified so that when more videos come out, you'll stay informed. So with that, we'll wrap it up for today. So see you, everyone.
Thank you, bye. Thank you, guys. Bye-bye.
Fernando.